Well, we will start our class. Okay, so we talk about the conservation of potential participants. And today I have a student who has workshops in the company. And our student just got surgery. So if you cannot come, let me know in comments. And we will get recording. And that I can send it to you. So I got recording every time, as you know. Sometimes I forgot, but pretty much I try to do them everything. And for the conservation of potential vorticity, if the flow is horizontal without divergence, then the relative vorticity plus the magnetic vorticity will be a constant. If it is a constant, then it has implication for the eastern flow and west flow. Situation is different, but the key, we need to understand what are the assumptions here. The assumption is non-divergence, pure horizontal flow. And these kind of situations are real-life situations. So when you look at these schematic diagrams, you need to know what are the assumptions behind. And for the wasted flow, the absolute vorticity cannot be observed because if the flow curve normal with cyclic vorticity, the Earth's rotation around parameter also decrease. So you got a cyclic curvature, planetary vorticity also increase. So the absolute velocity, absolute vorticity cannot be observed. Same thing for it to curve to the sun. So that means in the flow, you got wasted flow without divergence and without time change. If the system is in steady state, then it got to be done. Okay. And you look at a synoptic scale back. When do you see the flow pure wasted in total flow? We don't see that very often. We see the flow as curvature. You got to ask you. So it is not actually the case based on 4 figure 2G. Okay. And for the eastern flow, you can curve norward. Okay. When you can curve norward, you got anti-cyclic vorticity, and it can be compensated by the Earth's rotation. So it can be conserved. And if you move to the south, you got anti-cyclic. Okay. Move to the south, you got cyclic vorticity and decrease in planetary vorticity, so it can be conserved. So eastern flow can move south or north and still conserve the absolute vorticity, but not the wasted flow. Wasted flow got to be zonal unless it is deeply. And we know the wasted flow, wasted current is typical because in the Earth's atmosphere, the polar region is cold, the tropical region is cold. So you got the geopolitical weighting with low pressure to the north, high pressure to the south, so you got wasted current. Okay. And wasted current, as we talk about later, it can have oscillation. That's last year. That is what we'll talk about that later. So that is explanation for this figure block 13. And we also use the potential vorticity to discuss the flow over the mountain. Okay. Let me look at the flow over the mountain. Again, the western flow and the eastern flow, the characteristics will be because for the western flow, if we curve to the north, you got cyclic twist, and you also increase in correct armies. And the eastern flow just the opposite. So we talked about the western flow last time. So when we talk about the western flow in this situation, and really conservation of potential vorticity, and I would like to point out these based on shallow water equation. Yeah, we talk about that. Based on shallow water equation, that means the flow is incompressible. Okay. And we know that that is not true. If the air is lifted, you have adiabatic expansion, you have adiabatic cooling. So the density cannot be conserved, cannot be constant. As you go higher up, density decreases. Okay, and but this assumption is based on shallow water equation. So the density is considered as constant. So this is more or less like if you got water flowing over a small area, or you can consider this maybe like the water, the rock in the river, and then you have the water moving over the rock, and the flow is incompressible in this situation. So we do not consider when you talk about air over the mountain, density should change, but here we said density constant. So that is what idealized situation. Okay. And when you got the airflow move from the west to east, so near the first hill, at the first hill, the layer will be lifted a little bit. Okay. The column will be lifted a little bit. So in this case, you go ahead based on the conservation of potential vorticity. When it's lifted a little bit and then stretched a little bit, the radius decreases a little bit. So the vorticity will increase. So the potential vorticity is that the absolute vorticity divided by the day is the constant. So when you move here, it stretches a little bit as it encounters the mountain. Stretch a little bit, so it's been a faster. So vorticity increases. So vorticity increases, so it means you got cyclic curvature. You curve to the north. You got to curve to the north. But as you curve to the north, what happens? You got to have anti-cyclic to make it backward. And also, go over the deck string. Here, the force is a little bit so straight, but here the deck string. So horizontally it expands. So it's slow down. So anti-cyclonic situation. So anti-cyclonic. So here, hopefully not a little bit, and then because change in latitude, and also because the deck shrink. So anti-cyclonic moves until you reach the top. Okay, and after you reach the top, it still has the momentum to carry something. So if the fluids is not subject to forces, it's going to move in straight. So here, it moves in straight. When it moves in straight line coming down, it's the Earth's rotation effect is less significant. So it will acquire cycle. Okay. And also here the column shrink is going to spin up. Okay. So here you will have cyclonic curvature to make it move back. And but here until this point it will move straight. Once it moves straight, it means you overshoot the original location. You overshoot the original location with a straight line. Then that means magnetic velocity is going to increase. Magnetic velocity increase, further you will have anti-cyclonic. So it will move here and anti-cyclonic. So it will have a oscillation. But if you look at the easterly flow, the situation is different. So the key here is non-divergent flow in compression. The absolute velocity divided by the head of the fluids will be constant. So you got an easy read here. So here on the hill, you will be lifted so it straight. The top need to go up a little bit so it straight. So you got cyclonic on the here. So the curve here to the south. When you curve to the south, magnetic velocity increases. Okay, magnetic velocity increases. So what happens? Curve to the south, magnetic velocity increases. So you have to curve back. Okay, curve to the south, and then with positive velocity, it will have cyclonic rotation. Not only due to you will have cyclonic rotation, and in the meantime, the depth of the layer decreases. So that means here it will have anti-cyclonic rotation. Because the depth shrink, that means it's slow down the rotation. And in the meantime, it's moved to the south. You got lower velocity, so you got to come back to acquire velocity to be north, go higher. And here, coming down from here, straight. It's straight, so it's going to curve back. Okay, so both effect will make it to come back. And until here, reach this point, then here you got to rotate here. You got to rotate cyclone. So you come in here and then you get cyclone curvature because it's straight. Okay. And cyclone curvature, and then you move to the origin point. When you move to origin point, then you can anything move place. So you will have this kind of subject. So in this discussion, you need to look at changes in the depth and the change in height, both to be taken into consideration. So each of the below, you will curve this out and then into this. And if you look at this, can you explain the iPhone from the east and move over the mountain? So in Vietnam, you've got to coastal mountains. And if you got hurricane comes from the south of the sea, to the location, when you move over the mountain and then put to the east. Well, you will see tropical cyclone pretty much disappear over the mountain. The rotation increases, not a big trend. So, tropical cyclone, when it is moved over the mountain, you can see the upper level flow, upper level anti-cyclone, upper level divergence. At low level, it being distracted by frictional force and also become a dead string. So, it will decrease. All this tropical cyclone disappear over the mountain. And you only have upper level divergent flow. When you have upper level divergence, that means you have anti-cyclone rotation. If you look at it from the upper level chart, upper level you have divergence. So in the upper level, you have anti-cyclone rotation. So tropical cyclone move over the mountain, low level cyclone rotation disappear. And you see a upper level anti-cyclone. Then it's going to shift to here on the 50th. Then this start the spin because with the stretch. So for the tropical cyclone move from the east, it has tendency to generate new cyclone phase. So that tropical cyclone more or less will be deflected to the south. And over the mountain, looks like this here. And on the western side, it generated out of the hill. And when it generated out of the hill, go to the south right here. Okay. So these phenomena occur quite also for hurricanes. Tropical cyclone over central mountain range comes from the east over central mountain range. Those are disappeared. You only see upper level anti-cyclone. And after you move over the mountain, it form a new low level cyclone rotation to the south. Spin up. This kind of phenomena occur very much. Okay, I will stop here. For the discussion of the potential vorticity. And this, of course, is first approximation. Because we do not, we consider the group is inapproximate. But you can qualitatively explain certain phenomena. And for western current, we'll talk about a wave. We see what's to western current. And you got to see oscillation. And what's wave is a cancellation of absolute distance. So why does mass be weight exist in Earth? So we talk about low pressure center, high pressure center. You got a trough that reach. Okay. So you look at a little map, trying to reach. You see the trough, you see the reach. Okay. And all the time. And you see low pressure center, cold front to the east. And followed by the reach. That's right. That is due to acceleration of potential force. And if you look at the 500 millimeter chart, 500 millimeter chart, you can consider that is level of time, no convergence. Low level you convergence, upper level you get convergence. In the mid level, you consider that as a level of non-convergence. So at the level of non-convergence, absolute velocity is pretty much different. So for the Western flow, with that, you will have to get oscillation. You will have to get oscillation. It cannot curve to the north and continue, it got to go back. Once we push it to the north, velocity cannot be conserved, so it got to curve back to the south. Once you move to the south, it got to curve back to the north. So you will have oscillation. That's why we see not considered with low pressure nitrogen from nature. That is because it's situation of potential boost. Okay. So I will skip section 4.6 because really we don't look at that of isentropic surface. It is good for the research, but for most of the application discussion of weather and forecasts, I don't see anything showing isentropic occurrence. So I will skip this portion, and with only exception. I will talk about traffic potential system. I will talk about the isentropic barotropic potential system. Barotropic atmosphere. In that case, we use barotropic assumption, and in this case, vertical motion, Cauchy-One equation. Vertical motion is there, and a fluid is non-convergent under this condition. So you can have potential velocity pure horizontal flow without change in the air if no mountains. So you got this equation. Without mountains, is over flat, over which or over big ways. And you can write U and V in terms of strain function. Here. That's the definition of strain function. Strain function is, and the beauty of strain function is that you have U and V, east-west wind, north-south wind, and if the wind component could be combined into one parameter, that is strain function. Strain function cosine. So U is partial cosine partial y, negative, and that is normal wind. And V is partial cosine partial x plus v. So you plug this in, the velocity plug this in becomes Laplacian of cosine. So the velocity in this case can be written as a function of string function. Okay. So this much simpler expression. So the total observable testing is so follow the motion. So I define this. So this is horizontal affection of the potential system, and this is time change. So in this question, so cosine function is defined gradient cosine k plus that is that's a velocity, not velocity. So what is the duty in this question? 4.42. It only has one variable. Okay. And we assume density is constant and the flow is pure. Those are assumptions. You need to keep in mind, those are the basic assumptions. Density is constant and non-divergence. You have divergent conversion, and then you will mix up things here. So non-divergence, non-vertical motion, pure vertical. And you can write this as one equation with one variable. Mathematically, if you have one equation with one variable, and this is tendency vector. So that means based on the cosine function right now, you can predict change in the cosine function. So here, cosine function, V cosine is k plus gradient. So for this right hand side is only function of string function. So at any time, you can calculate right hand side. And once you got the right hand side, then you can that equals the tendency of the Laplace. So you will get the cosine function, the Laplace of the cosine function, not the change in the string. So you can do type integration to predict change in a Laplace. So this equation is our tropic one. And back in 1950s, the hurricanes, they tried to do the forecast of tropical cyclones. And how do they do the forecast in 1950s, 1960s? There is no there is not. So they use our traffic. Especially for traffic. So if you look, you read the paper, say, oh, we use our traffic model for the forecast of traffic motion and how the intensity change. How to do that? And this could be easily programmed. And using a calculator or you can use it on traffic model to do the prediction. But this equation, as I already said, it is good if there is no divergence. So you can apply these traffic model to look at prediction for the atmosphere without conversion and divergence. That's fine. Okay. At the top, at the surface, you have some convergence. At the high level, you have convergence. So where this equation can be applied to do forecast Primary mirror is the base location used for and this can be used to predict to the second based on traffic. Assuming known equations. Okay. So that is non-divergent horizontal mean right here. Okay. Any question? So I pretty much finished chapter 4. I said the isentropic of each of these. Any questions? Okay, I have about 14 minutes left. And the next topic I want to cover is a review of the moment and also a review of the way you meet. And that's why I emailed you for information. I got it from I forgot where I got it, but I got it from someone's teaching material. Searching the net for found those material for YouTube. So I downloaded it. But open source also against really weak in the week. And the reason I want to go through this is next topic will be concentration. Have you heard about concentration? A little bit. Did you take 412 or 416?
I'm in it right now.
Oh, you're taking
like touched on it yesterday actually.
concentration.
Yeah. It's interesting, yeah.
Yeah. The concentration theory. It is assumed the flow is close to the geotropic. And if the flow is geotropic, what does that mean? It cannot change with geotropic wind. No change. And geotropic wind, no convergence without convergence. And we say atmosphere is close to geotropic. 90% of the winds follow geotropic. How about the other things? The other 10% geotropic. That is the driving force for the change in the wind. That's why we use quasi-geotropic. The flow, the main flow is geotropic. And geotropic is equilibrium. It is equilibrium between pressure and force and force in an equilibrium. And if it is equilibrium, it does not change with respect to time. But it can be changed with respect to time when it is being forced out of balance. Once being forced out of balance, atmosphere will change to reach equilibrium. So that is a geotropic. We call this geotropic adjustment. Okay. Geotropic flow is equilibrium. No tangents. So that means it can be floating. And we know if it is floating, everybody will go. What causes the change in geotropic? So that's why we say quasi-geotropic. Only inflow, the main circulation, but allow geotropic. That will cause a geotropic wind. Also can force out of balance without any geotropic. Geotropic wind is equilibrium state. but it can be forced out of balance without agent. If you have to let it flow, can be forced out. So, if initial traffic and bar traffic, then it will be forced. So, how do you say about traffic? Density is a function of temperature, or temperature is a function of pressure. That's function. If it is our traffic in geotraffic, then the flow cannot be changed. But if it is geotraffic, but not our traffic, that's our function. Then things can be changed. Why? If the temperature is not a function of pressure, you will have temperature gradient. You will have temperature gradient. Wind parallel isomers, but along the isomers, you have temperature gradient. That means you will have warm compression. From thermodynamic energy equation, you have warm compression, you have cold compression. Then temperature is going to change. That's baroclinic atmosphere. So in the baroclinic atmosphere, the flow, the geotraffic flow, cannot be. Only in the barotropic atmosphere, the geotraffic flow can be. So if you got thermal wind, if temperature has an angle isomers, and isotope has an angle associated with isomers, you can have warm compression. Okay. Once you have collaboration and warm compression, temperature is going to change with respect to time. If temperature change with respect to time, you will force atmosphere out of geotraffic balance. So atmosphere got to induce a geotraffic flow to adjust back to geotraffic. That is baroclinic instability. So the geotraffic wind is important. That can affect geotraffic balance. And also the other component, even assuming you don't have geotraffic wind to begin with, the cold convection, warm convection, the baroclinic atmosphere, it will generate geotraffic flow to adjust the geotraffic wind to make it even. So that is the baroclinic instability of the quasi-geotraffic theory. And quasi-geotraffic means for the wind flow, I consider geotraffic. And geotraffic flow, I consider that as a secondary situation. So the main situation is geotraffic. But you can have secondary situation that is geotraffic. And the second situation you can have. So in the frontal zone, you will have secondary situation. That is baroclinic. So that's why I want to go back. And also, when we talk about the low pressure center, high pressure center, we're dealing with gradient. So that's why I want to do the review of thermal wind and gradient equation. Next, before I talk about fluctuation. and wave motion in the Earth's atmosphere. And the wave motion in the Earth's atmosphere, the main is the velocity wave. The velocity wave comes from the ratio of it can be easily divided. A velocity E divided the velocity rate by the negative. It's Norwegian. So those methodologies for Norwegian, they are the one that look at those velocity rate. Because in Thailand, they see velocity rate, they see constant, they see 1.1, and they try to explain something. If they explain something, saying that you have velocity rate, you got constant. You have time ratio, there is no connection. And the current parameter is a function of that. So mainly because current parameter, the Earth's rotation. So Earth's rotation on normal to the Earth's surface is a function of that. Because there is curvature. Near a low pole, the vorticity is twice the Earth's rotation. But away from the low pole, the vertical component tilts. So you got the times sine phi. So the rotation in the vertical component, perpendicular to the Earth's surface, the curvature changes with respect to that. You got change, absolute velocity can change. That means if the airflow move to the north, increase in the planetary velocity, the planetary velocity can increase or decrease. Once you move to the south, it can decrease in the planetary velocity. So whenever it can curve back to the cyclonic rotation. So you have wave motion. You get wave motion. Okay. So with no mountains. You got waves as well. You got waves those coming from the west. And then you move to the north, increase in the planetary velocity. So you got to have anti-cyclonic rotation. So flow got an enhancement. Once move overshoot goes to the south, the planetary velocity decreases. It got to have cyclonic rotation. So it got to curve back to. So you got velocity with first much. You do relation. Absolutely. Complex situation we know. So this in the time I'm telling you it is not certain, but it got to curve back. And as it go to the north, it got to curve back. And you move to the south, it can actually go. And I think I pretty much explained the situation. And I know I was in a PhD student. One PhD student is take communication thing. Well, you gotta take communication and read the parts. And one outside member bullshit analysis. Well, our PhD student there is they can derive equation, they can memorize all the equation. Posing all the equation, memorize. Here, you can write the equation on. But the outside member equation. I don't want to see any equation. Don't put equation on Just answer my question. Why you have us? First, it's a risk. Conservation of possible disease. If no convergence, relative history plus relative history calculates. And the relative history is a function. So if the flow move to the south, then relative history can be changed. Move to the north, you got to get index of convergence. Move to the south, you got to get cycle of history because relative velocity plus absolute velocity should be. That's why you got to do it. That's the answer. You can answer it in 5 minutes. And the student put down about the one thing look at all the equation. That means the student is so the motion outside member you cannot answer that's the basic. That's why I had no operational factors. Okay, what's made up? Well, PhD student cannot answer or answer. You gotta take it. So the easy equation always easy. So those concepts are when I teach the class, I always want to be sure you understand. Okay, I'll start.
Thank you.
Okay, yeah, sure.
See you Friday.
Yeah.